In this example, we will study permutations with repetitions not allowed. In Part A, how many ways can the letters in the word see be arranged? Set up columns for the first letter, second letter, and third letter. The first letter can be S, E, or E. These are the options for the second letter. And these are the options for the third letter. We can form 6 words out of the letter tiles. We have a problem. There are duplicate words. The word SEE is indistinguishable from the word SEE, so it's incorrect to say there are 6 words. There are only 3 permutations of C: SEE, ESE, and EES. We can also solve this problem using the fundamental counting principle. The number of ways to arrange n objects, of which r objects are identical, is n factorial over r factorial. There are 3 letters altogether, so 3 factorial goes in the numerator. There are 2 identical e's, so 2 factorial goes in the denominator. Expand 3 factorial. Stop expanding at 2 factorial since it cancels with the denominator. The answer is 3. Note that this is a single case permutation because we can answer the question with a single term. Rewrite the answer. There are 3 words that can be formed: SEE, EES, and ESE. Now we'll visualize this using permutation tiles. In our sample set, use a blue tile for S and 2 red tiles for E and E. Set up positions for the 3 letters. There are 3 letters available for the first position. There are 2 letters available for the second position. And there is 1 letter available for the third position. Multiply the numbers to get 3 factorial. The permutation tiles can go in any position, so it's possible to get repeat arrangement since we have identical tiles. For example, if the red permutation tiles are interchanged, we get an identical arrangement. Identical permutation tiles can be repositioned, so we need to divide out the repetitions since there are 2 red tiles. This gives us 3 factorial over 2 factorial, which equals 3. In Part B, how many ways can the letters in the word Mississauga be arranged? The word Mississauga has 11 letters, which can be arranged in 11 factorial ways. There are 3 repeated letters: 2 A's, 2 I's, and 4 S's. Divide the total arrangements, 11 factorial, by the repetition arrangements, 2 factorial times 2 factorial times 4 factorial, to get 415,800. The answer represents the number of unique words that can be formed with no duplicates. This is a single case permutation because we use up all of our letters with a single draw from the sample set. We do not restock and redraw, and there is only one term. We can visualize this by setting up 11 positions and using permutation tiles for the letters. There are 11 options for the first position. There are 10 options for the second position. Fill in the options for the remaining positions. Multiply the numbers to get 11 factorial. The permutation tiles can go in any position, so it's possible to get repeat arrangement since we have identical tiles. For example, if some of the red permutation tiles are interchanged, we get an identical arrangement. Identical permutation tiles can be repositioned, so we need to divide out the repetitions. There are 2 blue tiles, 2 green tiles, and 4 red tiles. Now we'll move on to part C. A multiple choice test has 10 questions. 3 questions have an answer of A, 4 questions have an answer of B, 1 question has an answer of C, and 2 questions have an answer of D. How many unique answer keys are possible? Before we begin, write out the sample set. We can arrange the 10 letters in 10 factorial ways. However, there are 3 A's, 4 B's, and 2 D's, so we need to divide out the repetitions. Divide the total number of arrangements, 10 factorial, by the number of repetitions, 3 factorial times 4 factorial times 2 factorial, to get 12,600. The answer represents the number of unique answer keys that can be formed with no duplicates. This is a single case permutation because we use up all of our letters with a single draw from the sample set. We do not restock and redraw, and there is only one term. We can visualize this by using permutation tiles to represent the letters. There are 10 options for the first position. There are 9 options for the second position. Fill in the options for the remaining positions. Multiply the numbers to get 10 factorial. The permutation tiles can go in any position, so it's possible to get repeat arrangement since we have identical tiles. For example, if some of the blue permutation tiles are interchanged, we get an identical arrangement. Identical permutation tiles can be repositioned, so we need to divide out the repetitions. There are 3 blue tiles, 4 red tiles, and 2 yellow tiles. Now we'll move on to part D. How many pathways exist from point A to point B if the only directions allowed are north and east? Before we attempt this question, let's look at a few pathways. One possible pathway is north, east, northeast, north, and east. Another possible pathway is east-east-north, east-north-north. All possible pathways will be a word with 6 letters, 3 E's and 3 N's. Divide the total number of arrangements, 6 factorial, by the repetitions, 3 factorial times 3 factorial. The answer represents the number of unique pathways that can be formed with no duplicates. Now we'll move on to part E. How many ways can 3 cars, red, green, and blue, be parked in 5 parking stalls? Before we solve this, let's look at a few examples. One possible arrangement is red, space, green, blue, space. Another possible arrangement is space, green, red, blue, space. All possible parking arrangements will be a 5-letter word with repeating S's for the spaces. Divide the total number of arrangements, 5 factorial, by the repetitions, 2 factorial, to get the answer, 60. The answer represents the number of unique parking arrangements that can be formed with no duplicates. Now we'll move on to part F. An electrical panel has 5 switches. How many ways can the switches be positioned up or down if 3 switches must be up and 2 must be down? Before we solve this, let's look at a few examples. One possible arrangement is up, up, down, down, up. Another possible arrangement is down, up, 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 down. In both cases, we have a 5-letter word that has 3 U's and 2 D's. Divide the total number of arrangements, 5 factorial, by the repetitions, 3 factorial times 2 factorial, to get the answer, 10. The answer represents the number of unique switch arrangements that can be formed with no duplicates.